Hi, I'm going to talk about a machine learning demonstration today where we're looking at optimizing a resource trading network where we have a series of resources or a collection of resources that we can trade and move around in order to optimize how those resources are used and in conjunction with what other resources. My name is Martin Madsen. I have a PhD in experimental physics and 16 years experience working with sensors, data collection, data analysis, and predictive model building. The scenario is starting with a collection of equipment or resources of one form or another. Imagine that these resources are grouped together geographically or logically. It depends on how we want to group them, but imagine that these are geographical groupings. And some of the resources are grouped together in ways that are less than optimal. Maybe the medical devices in dogs down in the bottom right-hand corner is not such a great grouping. But there is a different object, the vaccine dispensers, that maybe if we could trade the dogs for the vaccine dispensers, that might improve the overall usage of the group. So we make the trade, and then we discover that this is an improved group, that the medical devices and vaccine dispensers together are both more useful than they were in the previous configuration. We'll take into account some issues with as we think about trading resources. Some of the resources aren't tradable. The power plants or factory floors don't easily move, so we'll have the ability to fix some of those down. And so we'll think about, on the cost side, the resource mobility. How easy is the object to move? How much does it cost to transport? How far does it have to move? And balanced with that is the payoff for moving. How much improvement do we see in our resource allocations by making the trade? To demonstrate this idea of a resource trading network, we're going to use the idea of trading cards. Imagine we have a collection of different poker tables, and we have people sitting at these tables, and that they look at their cards in their hands and say, well, if I could just trade cards with somebody else at a different table, then my hand would be better than it currently is. I know this is frowned upon and probably illegal in real casinos, but imagine that we're playing in a friendly way, and that card trading would be an okay thing. So the first step is that we need to know how a hand configuration is scored. What hands are better than other hands? And I wanted to make this a neural network trained scoring. Of course, it's straightforward to score hands in a straightforward way, given an algorithm. What is a high card? Is there a pair? Is there multiple pairs? And we can score each configuration of hands on a scale of 0 to 9, 0 being no pairs, just a high card, and 9 being a royal flush. By using a neural network, what I'm doing is preparing for configurations that aren't easy or straightforward to score by hand, with a known algorithm. So I want to use the neural network to train the idea of a pattern of objects, not necessarily a specific number of objects in a specific set of positions. So what we're going to do here is change the poker hand representation from cards into a pattern, and then use the neural network to image those patterns and learn the deeper underlying meaning in each of the patterns. So imagine I start with a hand here. I've got 5 cards in my hand, and I will map those into entries in a grid. So now the ordering of the cards in the hand doesn't matter. Just which cards, what numbers do I have, and what suits do I have, and I map those into ones in an array that's 4 by 13, 13 cards in each suit. In order to work with the neural network, I need to embed this into a larger image that's symmetric, so I chose a 16 by 16 grid and embed the card data into that 16 by 16 grid, giving a little bit of buffer space around the edges of the card data itself, which will be beneficial as we do our training. And then the last step is I turn this into a black and white image, a binary image, where ones represent the card locations and zeros represent all the other space. So this is the same representation, and now it's fairly clear to see that a pair would mean that I have 2 white dots vertically on top of each other. Maybe not necessarily next to each other, but in the same column. And then a straight would be cards that in sequential columns. So here's an example of a handful of different hands. For the upper left-hand corner, there's a full house. There are 3 8s and 2 kings along with the 9. On the second row, the far right column, where there's 3 hearts and 2 diamonds. There's no pairs, there's no straights, there's no runs. So that's just a high card hand. So this is a variety of different hands. In training our neural network, I chose a collection of hands that had 5, 6, or 7 cards, which correspond to the range of possible hands for a Texas Hold'em configuration, whether you've got 3, 4, or 5 cards out on the table. I'm using a convolution neural network. This is a modified network from the Linnet configuration. It consists of a convolution layer, a 5x5 kernel, and 20 filters. This detects underlying edges and edge patterns, a hyperbolic tangent activation layer, a pooling layer, and then I repeat the convolution with 50 layers, a second activation layer, a pooling layer, flatten it, and then do fully connected 500 nodes, another activation layer, another fully connected nodes, and then a softmax output. So it's a fairly standard small convolution neural network. And the convolution layer means that I can pick out the features where the patterns are based on runs or pairs or 3 of a kind or 4 of a kind. I train the neural network on a collection of about 4 million different unique poker hands, the 5, 6, and 7 card hands, with the distribution that looks like this, where there are primarily 0 and 1 pair hands. But there are a significant number of hands in the higher ranks, all the way up to there are 52 different royal flushes hands. And the reason why there are multiple of these is because I can add these additional 6th and 7th card, which don't change the hand scoring, but make it more possible. They make more possible hands. I train the neural network using a CUDA-powered 4-GPU machine. We train over this course of 600 epochs. And you can see in the graph here the in-sample training accuracy rapidly approaches 1, and then over the course of the last 400 epochs eases its way into an in-sample accuracy of 99.97%. I reserved about 1 million unique hands, different from the training data, in order to verify the out-of-sample performance of the neural network. The distribution is very similar, although there are fewer numbers of all the different possible hand ranks. And this is the convolution, or the covariance matrix that shows the performance of the model on the test data. I have about a 99.9% accuracy, and you can see that most of the predicted and actual classes line up with each other, except for the 8 and 9 for the hand ranks, that being a straight flush and a royal flush, and they're mostly confused with straights and flushes. So it's not super surprising that 8 and 5 and 9 and 5 would be confused with each other, and then 8 and 9 also would be confused because the royal flush is just one specific instance of a straight flush. So these are also fairly infrequent hands, and so the fact that they're not scored as accurately is not a big deal because they're not going to happen very often. So now that we have a way of scoring hands, we're going to move to how we're going to go about trading hands or swapping cards between players. We're going to build a scenario where we have 13 different casinos that we're working with. 12 of them will be in Las Vegas and 1 will be in Atlantic City, so it has a significantly larger distance to travel, which means that we shouldn't have very many cards that will be traded between the Vegas and the Atlantic City casinos. And then each casino will have 3 different poker rooms. It will have 2 tables in each room and 2 hands at each table. So there's a possibility of trading hands at the same table, which is a very low-cost trade because we're not traveling very far. And then trading within casinos might be less cost, and then trading between casinos now is starting to incur travel costs between geographic locations. And I actually mapped out these casinos geographically, and I'll show later on where the casinos are at and how the cards are traded between the casinos. Each card will give, has a face value, and we'll also give it 2 additional parameters. So we'll give it a transportation cost. It's the cost of moving the card per kilometer, and that'll be a random number distributed somewhere between 0 and 5 or 6. And then each card will also be given an occupation level. And so cards that are occupied mean that they can't be moved. So we'll make it a very high number for table cards that can't be traded. But this might be something, a parameter that could be set by a user. For example, if you have several very good cards that you don't want to trade, you could imagine setting the occupation level significantly higher, saying I don't want to let go of these cards. So I'll run through a demonstration of how we do the trading network and how we optimize the trading network. We're going to start with the configuration, this configuration of 10 different hands. And you can see that the 10 hands that we're starting with are not very good. We have 4 different hands that just have a high card or a score of 0. We have 3 hands that are a single pair, 2 hands that are 2 pair, and 1 hand, that lone hand in the lower left-hand corner, that's a straight. That's a decent hand to start with. We'll start by looking at these 2 hands and imagine what we do or how we would work with a trade of cards between those 2 hands, and then generalize it to the rest of the hands and then run about 3,000 different trading possibilities and see what happens to the network. So in these 2 hands, there's one card, the 9 of spades, in the top hand that has a high occupation number, so that card can't be traded. It's a table card. And we're going to be trading between the Excalibur and the California casinos so that there's a little bit of transportation cost associated with moving between them. Right now, the score of these 2 hands together is a combined total of 6. 4 for the straight and 2 for the 2 pair. So what if we were to trade these 2 cards? So we'll randomly pick 2 cards out of one card out of each hand and say, let's try trading these 2 cards. So we'll swap the 2 cards, and when we rescore the 2 hands, we have 2 pairs still, nothing changed in the top hand. And now the bottom hand only has a pair. And so our new total score is 3, which is significantly less than the 6 that we had. But we still might trade it. And whether or not we trade those cards anyway, even though it's not good, is determined probabilistically. What we do is start early on, and what I'm plotting here is the number of iterations that we consider swapping cards, and we'll run all the 3,000 of them. And on the vertical axis, I've called the pseudo-temperature. This comes from a Monte Carlo anneal from solid-state physics. The idea is that if your temperature is high, your pseudo-temperature is high, you still might trade even though it's not a good trade. So the probability of keeping bad trades is high early on. And then as time goes on, as we ramp the temperature down, the probability of those bad trades happening goes down significantly, all the way down to the point where we're not making bad trades anymore. What we found is that this helps get out of sticking points where doing trades that might not be good early on might be better for the overall configuration later. And so if we allow those trades to happen early on, it gives us a higher probability of reaching an optimum solution later. So going back to a couple of hands here, we'll say we didn't keep that trade. It just turned out probabilistically that we chose a random number and it said we roll a dice and it says don't keep the hand. So let's try a separate trade. What if instead we trade the 10 on the top for the 9 of clubs on the bottom? All right, when we make that trade, now the top hand has got a full house, 2 5s and 3 9s. The bottom hand still has a pair of 10s. It's not as good of a hand as it was before, but the sum total of both of them is now 7 as opposed to 6. So the overall configuration of all the hands together has improved. And this is a collaborative trading network where we're trying to make everybody, or the sum total of everybody, better. So we're likely to keep this trade because the end result is better off than the prior result. So we'll put these cards now on the network where we're now looking at these casinos in Las Vegas. There's a collection down on the Strip and then a handful more up in the Arts District. And we'll see how we'll run this through the trading algorithm, run 3,000 different iterations, possible swaps, and see how the cards move after that. So we track the total score of all the hands together as a function of iteration number. And you can see on the left-hand side, as we start between 0 and 1,000, the temperature is fairly high, and so we've got a lot of up and down movement, where some of the trades are getting better and some are getting worse. But the general trend is starting to increase, although it might be increasing slowly. And then as the temperature ramps down, the number of downward movements decreases and the number of upward movement just slowly eases in until at the iteration 3000 we've ended up with a score of 41 where we started with a score of 11. So we've more than quadrupled our total score for the total number for all the hands on all the tables. And this is what the card swap looks like, where we've got cards trading between casinos, cards trading within casinos. However, none of the cards are being traded to Atlantic City from Las Vegas, which is not surprising because the transportation cost of getting the card from Vegas to Atlantic City is fairly high, given that we've added a cost of about 1 unit per kilometer, and so they're just not going to happen. So to remind you what we started with, this was our input hand. These were our input hands, where we've got a couple of pairs and a couple of 2 pairs. And this is what we've got at the end, where the lowest hand now is a single pair. And we end up with 3 full houses, a handful of straights, a handful of flushes, and a handful of double pairs, 2 pairs. So overall, everybody except one hand, everybody except one hand, the upper left-hand hand, ended up better than what they started with. It was 2 pairs to start with and 2 pairs to end it with. But all the other hands improved or made significant improvement. Even that straight hand in the lower left-hand corner, our best hand from previously, it was a straight before and it became a flush, and so it also improved. So in summary, I built a pattern recognition neural network where I vision the poker hands as images, as configurations, as opposed to being characters and cards. And then once we trained the neural network, we showed we had better than 99.9% accuracy in sample and out of sample using the neural network to score the hands. And then we developed a Monte Carlo simulation that allows us to swap cards, which shows that over the course of trading, the course of running the algorithm, we can significantly improve the overall score of the hands. And then after we trade, everyone ends up better, or at least in as good as they were, or in a better situation. Thank you very much for listening today, and if you have questions, comments, or further conversations, please contact me on LinkedIn.